set of data because the person who's collecting this data thinks there's n separate variables you can represent each data point. But in practice, you think that k is enough, and how do you, well, it already says live now, so there's something is happening, but it might be just blank. I haven't checked it. So it's a dimensionality reduction, except that you are constrained, and you can see it in the problem formulation. You want these matrices with lower dimensional space, W and H, to be all non-negative. All the entries are either 0 or positive, right? So that's the constraint. And why do we want that? Imagine this is Netflix data, right? Some sort of Netflix data, and the ratings are from 1 to 5. Or I don't know what these days are, and then your PCA returns you minus 2.7 as your lower dimension. It doesn't exactly make sense to you. It has interpretability disadvantages. So there are some applications where non-negative matrix factorization make more sense. And also I should say this, factorization is a misnomer because these things are actually not equal to each other. Even though I use the equality sign because of PowerPoint restrictions, this is just an approximation within some norm, right? There is an error, and we're trying to minimize that error in Frobenius norm, which is the objective function over there. So it's just an approximation. The exact factorization is not possible unless you have lots of compute time. It's an NP-odd problem. So you have to understand what is the issue here. You're given a single input and you try to recover 2 inputs. That is naturally a little ill-posed. So a lot of the algorithms are therefore iterative. So you initialize one of these matrices. There are good initialization methods. Some of them use PCA to initialize, or there's just random. There's schools of thought that say random is just as good enough as anything else. But that's a separate area of research. Assume that you have an initial age, somehow initialized by some simpler algorithm. And what you do is, given an h, now you have 2 variables that you know, h and a. Now you can solve for w, right? That is much more well posed. And then once you solve for w, now you're going to fix that w and solve for h. So this is the alternating updates framework. A lot of algorithms follow the same framework, right? So what do they do? Multiplicative activate, alternating least squares, and alternating non-negative least squares. One of the most popular ones that is in general good enough. The first algorithm, this is also historical. It started with multiplicative update, was perhaps the first paper, pretty high impact, but it's not a highly convergent algorithm. Alternating least squares, what it does is, at every stage, it solves the least squares problem. Unfortunately, it doesn't have any constraints, so it sometimes returns you a w for the first step, for example, with negative entries. So what it does is brute force sets them to 0. And then goes to the next stage, hoping that it will actually converge somewhere meaningful. A little more meaningful way of doing this, more principled way of doing it is, instead of solving an unconstrained least squares problem, at every iteration you can solve a constrained least squares problem, which will never give you negative entries, so you're not brute forcing anything. Right, and a couple of papers that you can read about this, but just again, going back to our original machine learning intro, never forget that this is, I'm just giving you one technique to solve a problem. So non-negative matrix factorization is a family of algorithms. You can apply any one of them, and you need to understand your constraints. This one is a little better quality approximation you'll get, but typically more expensive. Some online algorithms, like stochastic gradient descent, that uses much less memory, might be good enough for your purposes, and might be the only choice you have given the environment you're running these things on. So, don't think that this is the only game in town. But this is one very efficient game in town if you have enough memory to store these intermediate values. So what is the main computation behind here? Basically, you're doing a bunch of matrix multiplies, right? For updating W given an H, you need to calculate HH transpose or AH transpose, and H and W are somewhat replaced for the second iteration. So what's going on is really you are remember this shape of these matrices. You're either multiplying a tall skinny matrix with a squarish, almost rectangular, but not that skewed matrix, or you're making an inner product of these skewed matrices. So these are the two operations. And we know some algorithms, how to optimize them, and how to avoid communication in large scale. So that's one line of research that has explored this problem. Just the characteristics. In general, you can assume W and H are more or less dense. But for some interpretability reasons, sparsity is occasionally enforced, meaning that you want the output to, you penalize the objective function in such a way that instead of finding explicitly minimizing the difference between A minus WH, it minimizes the difference A minus WH plus penalty terms, the number of non-zeros in the W or H. So it basically tries to recover the most parsimonious explanation for the data set. And it's again goes back to interpretability argument. So that they might be sparse, but you can assume it's dense, usually because the sparsity there is not high enough to take advantage. The input, though, can be sparse, and often is. A lot of the test data sets people play with, like the Neves data, Newsroom, the conversations and emails. So basically, a very standard data set for this problem. It has a lot of News posts and the words in them, the frequency of them. So it's pretty sparse. Each post only certain words exist, and the other ones don't exist. So the input can be sparse and often is. And so, what's happening is, just to give you the dimensions of the problems, these are the computations you end up doing. In parallel, how is this thing done? Basically, you need to optimize these inner kernels, the WA multiplication or HH transpose multiplication, and the algorithms that are developed for this go back to the communication avoiding algorithm. Some of them Jim talked about, right? The caveat here is A is usually significantly bigger than H and W. Otherwise, we would probably not be doing dimensionality reduction to begin with, right? The K dimension that we're trying to recover is significantly smaller than the apparent dimension in the input, which is N. So A is much bigger. So instead of thinking about this as a blind square by square matrix multiplication, you have to understand that communicating A is the most expensive thing, and you're better off just rotating the input, the output, sorry, W or H. That is usually the main idea behind this work, and the algorithms presented in this paper, they're cited down, actually covers various alternating update frameworks, meaning that it will do alternating least squares, multiplicative update, alternating non-negatively constrained least squares, because they all have the same structure. Okay? And then it will automatically choose the best data and algorithm description. So that's one algorithm for matrix factorization. And the takeaway is, if you know how to optimize the inner kernel expensive routines, you're probably good enough for this. You might not need to change the outer algorithm too much. There's enough work here to justify just doing what we called implicit parallelization. Okay, moving on, clustering. So clustering, I'm going to talk a couple methods, but before that, just I want you to understand what's the problem. Many of you know you're given a bunch of data points and no additional information in general. You're trying to group them together in certain number of groups. There are some algorithms that will determine the right size of the right number of groups for you, and there are some that will require you to give some sort of K. Right? The most famous example probably is K-means. Everyone probably has heard about that. It's called a centroid-based algorithm, where you initialize to K centroids and then figure out distances to these centroids. Everyone determines who's closest to which centroid, and then you redefine centroids, and until convergence you iterate. Right? So this is one class of algorithms that once you plot your data set, if they are actually in some spatial dimension clustered, usually they make much more sense. You have coordinates and they work very well. When you have data sets where your clustering definition is slightly different, and imagine the commonly used example here is you have a circle of points. They're really close to each other, densely connected circle, but nothing inside the circle. But there's a separate cluster inside the circle. like a big circle around, and then there's a cluster of points inside. So the k-means will not actually find you what you think is the right clustering, which is the points around the circle themselves will be one cluster, and points inside will be a separate cluster. But k-means will not find you that. A couple of algorithms will. Agglomerative methods, for example, single linkage clustering will likely find that, which basically looks at the distances between points, and if there's any 2 points that are close to each other between different clusters, it just merges those clusters in. So it will find that circle very well, and it will likely not connect it to the inside different cluster. But alternatively, spectral methods will find it too. So in general, there's lots of methods, and depending on your application, you might need to make a wise choice using your domain knowledge, right? And some of this domain knowledge is already out there, meaning that there is a reason certain fields use certain algorithms a lot, right? So the field I worked on, some biology, protein clustering, they really like the flow-based methods that I'm going to talk about, the macro clustering, because that works for their problems for reasons they understand very well. But by contrast, some of the methods only make sense for a different set of domains. Okay? So spectral clustering, this intro applies to a lot of more clustering methods. These are the kind of methods that usually first need to calculate similarities, distances between points. Right? This can be given to you, like your input might be just the distances between points, but sometimes it might not be given to you. You might just get coordinates or just feature sets. So this can be an expensive process sometimes. If your input is just like in the non-negative matrix factorization, all you get is samples and features, then you need to actually compare every sample to each other to see how much of their feature sets intersect, and then you have to choose an appropriate distance function. There's lots of them. So cosine similarity, Jaccard index, and it really depends again on your application. Some of them are based on rank, some of them are based on absolute value, and some of them have connections to geometry. And I throw in one that's not particularly known, logarithm of odds, lot score. So that's used in, for example, in some genetic mapping problem, right? So there's lots of different distance measures. Some of them make sense to a lot of problems. Some of them only make sense to certain domains. And then once you compute those similarities, you can treat them as distances, right? Usually the inverse of them is the distance, right? So if they're really similar, then the distance is small. So you can do 1 minus or e to the 1 minus distance, whatever is going to create you some sort of function where the large values become shorter distances and vice versa. And then there's the question about, then are you going to just use that information, or you're going to sparsify that graph that you just created based on similarities? By the way, I talked a little bit about graph, but does everyone know what a graph is? Okay, so graph, in short, is just an abstraction used in computer science to represent points and their relationships, usually binary relationships, but there are certain graphs that are hypergraphs that can represent non-binary relationships. And then, once you represent similarities as edges and samples as vertices, you get a graph. That's what we're talking about here. So you can just use the input you got from the similarity directly, and that will be a fully connected. You can put a threshold. Let's say everyone can be connected to at most k neighbors. That will be a KNN graph. Or you can say that I'm going to cut a threshold that only the edges above certain threshold will be included. These are, again, depending on the application, makes sense. Sometimes you might have to do this because of your budget constraints. If your n is big, n squared might be too much to store anywhere. So you might have to just enforce some sort of threshold anyway. And actually, our next algorithm will have to do that. All right, so what's the class intuition? This actually will be covered in the partitioning class as well. The minimum cut of a graph, you represent this graph and find the minimum cut, it will actually give you, divide your graph into 2, and that's almost optimal for this problem. And now you can recursively do that, right? You can basically identify the minimum cut, remove that edges in between, so you split your graph into 2. So just to go back, let's say the minimum cut here is these 3 edges that connect these 2 clique-like structures. There's like a 5-vertex densely connected group on the left and 4-vertex densely connected group on the right. The minimum cut will likely find such that these 3 edges that connect these 2 groups needs to be cut. And then if you recursively continue and think about a large graph, that will find you pretty good clusters. The problem is identifying a minimum cut is NP hard. So the actual algorithms are significantly different than recursively finding the minimum cut explicitly. And they are based on the spectral clustering. The spectral part of it is based on this idea called the Laplacian. So it's worth spending a little bit of time because it's going to come in the graph partitioning class as well. So let's say W is your adjacency matrix, meaning that for every edge there is, Wij it has a value. And in this case, forget about the weights, just say it's unweighted graph. And if there is an edge between vertex I and vertex j, then Wij is 1. If it isn't, it's 0. So that's W. And the Laplacian in the basic case is defined as D minus W, and D is a diagonal matrix where every diagonal entry is the degree of that vertex. So now you can basically see why the Laplacian is the way it is. On the diagonal is the degree of each vertex. The first row or column has 2 because the first vertex has 2 adjacent edges to it. And the second column or row is 4 because the second vertex over there you see has 4 edges connected to it. It's by the definition, right? And then the minus ones come because it's D minus W. You're subtracting the values of the adjacency matrix from the D, so you get a bunch of minuses. It looks like a little arbitrary to define these Eniv entity, but this thing has a lot of algebraic properties that allow us to come up with theorem and meaningful algorithms on. Right? And this is the unnormalized graph Laplacian. There's 2 normalized graph Laplacian definitions, which I recommend, by the way. And there are slightly different versions of them. Even though I'll describe mostly unnormalized, if you ever try to solve spectral clustering in practice, I recommend you use the normalized symmetric Laplacian because the properties of it make it easier to solve in practice. Right, so, and it has to do with how you solve eigenvalues, and let's get to that. So here are the steps. 1 spectral clustering algorithm. Again, there's 3 different ones at least, if not more. This one is the one that uses the normalized Laplacian, normalized symmetric Laplacian. So you basically first construct a similarity graph and compute the normalized graph Laplacian. And then you find the k smallest eigenvectors of this Laplacian. Okay? So what are we trying to do? We're basically given input in some space, and then we're trying to transform it to a different space using this eigen decomposition. Well, the idea is in that space, all these clusters will be much more apparent. Right? And that's, in fact, for a lot of graphs, that is true. And I'll explain the ideal case where there's a bunch of connected components, and this algorithm obviously will find it directly because that's where the whole intuition comes from. So you will be now transforming your input. This is almost like dimensionality reduction, right? You can see that now you were given n by n similarity matrix. Now that the second dimension n has shrunk to k with the k smallest eigenvectors. And then you run some sort of standard clustering algorithm, let's say k-means, on that data, where you got the eigenvectors after you normalize the entries, and then you will be able to recover the clusters. So why does this work is, this is the ideal case explanation, which I think mathematically the most meaningful one. Let's say you have these 2 connected components, very simple problem, right? But general problem is usually approximations of this. There's a well-connected component, a few edges between, another well-connected component, or lots of them, right? That's what you're trying to recover. In this case, what will happen in your Laplacian after certain correct permutation, and again, spectral clustering won't need to find the permutation, but let's say it's, for ease of explanation, it's nice to describe it in the correct permutation. This creates a block diagonal matrix, right? And in the real case, there will be a couple of extra entries in the off diagonals, but there'll be well densely connected block diagonals, and your job is to recover this block diagonal structure. And so what does the algorithm do? It tries to, it uses the smallest, eigenvalue, right? So eigenvalues are all non-negative. So what is the multiplicity of the eigenvalue 0? It is exactly the number of connected components. So think of this, what is the eigenvalue problem? LV, first find that vector, eigenvector V, such that LV equals lambda V for some lambda. Okay, fine. So this first vector will give you an eigenvector. Why? Because if you multiply it with the Laplacian, it will give you 0. So it's the eigenvector corresponding to the 0th eigenvalue, right? But the second one gives you the same thing. So that's also an eigenvector corresponding to the 0th eigenvalue. So the number of eigenvectors you're going to find is exactly equal to the number of connected components. You can generalize this thing. And in the real case where this is not completely disconnected, there'll be close approximations that then you'll be able to cluster this part of the data much more easily than clustering that part. It kind of looks like a, both of them look easy in this case. But in the real case, the spectral transformation often makes your life easier. And we'll come back to a couple of eigenvalue plots in the partitioning class, because that actually uses the same idea. Okay, that leaves us with one real problem, which is how do we compute k smallest eigenvectors, right? K eigenvectors that correspond to the smallest eigenvalues. That makes more sense, but it's a mouthful to put on the title. The often used algorithm is called Lanczos. It's an iterative algorithm where the inner loop, the expensive part is the sparse matrix vector multiplication, which kind of, we know that it is minimal data reuse. We have already seen sparse matrix vector multiplies issues. It's less than 10% of the peak. In fact, it might have dropped with the peak increasing and the bandwidth is not catching up. And to optimize this and minimize communication, we do graph partitioning. So there's a little bit of chicken and egg. But there are other algorithms other than Lanczos. Some of them are numerically unstable. They still use SPMV, power iteration. You can think of Google's PageRank. LOT-PCG is one of the state-of-the-art methods where instead of using sparse matrix vector, it uses sparse matrix multiple vectors. It tries to recover all k at once, right? So it iterates a much bigger space all at once. So there is some more data reuse potentially than SPMV. The algorithm is more intricate though. And convergence may or may not be just as good as Lanczos. But in the end, when you need to implement this, you probably just want to use something existing. ARPAC is one such library. It implements what's called a reverse communication, meaning that it implements the numerical logic for the algorithm, and then you decide, you implement SPMV for it. So now you can just do all these tricks about optimizing SPMV. If it's distributed, you can distribute your SPMV the way your data suggests it should be. And you won't need to worry about numerical parts. The ARPAC will call your SPMV code iteratively and do it. Right? It's a nice way of writing software, but one way of writing software. And in fact, the only code that's I've seen for spectral clustering in parallel uses ARPAC's parallel version, and you can find it in that link. It's been out there for almost a decade by now. I think it still compiles. All right, questions? All right, let's move to another clustering algorithm, because it's one of those things that I, off the record, want to say dime a dozen. The clustering algorithms, there's so many. Just giving one sample is probably too skewed. So this is one that's really popular among biology people, but the idea behind it is actually intriguing as well. So, I mean, this is the standard cluster definition. You want your clusters to be well connected within each other and sparsely connected across. That's the motivation behind pretty much every graph clustering algorithm. But MCL's main idea is if I start doing random walks on this graph, they will get trapped within the clusters more often than not. That's also another way. Some algorithms that are based on local clustering that are currently popular they're different because, for example, in that case, what they're trying to do is, I only want to find out the cluster around this particular blue vertex, and I don't want to spend time iterating on the red part. So they do the random walk starting here. But this is for the case where you try to recover the clustering structure of the whole graph. So, you start random walk, and you start accumulating probability, like how much of it is staying, and then you have to do certain pruning attempts for computational reasons, because if the graph is well connected, probability will go from anywhere to anywhere eventually after enough steps. Then that will create a dense intermediate matrix that's computationally infeasible. Instead, you can basically say, after every couple of steps, I'm going to prune the small entries to 0, because there are probably sparse connections between different clusters. And there's actually two ways of removing them. One of them is it forces, it's called inflation. So let's explain what is going on. That's actually what happens on a real input. First, you do, at every iteration, you're recovering certain levels of cluster structure, and eventually you'll get to an output where there's disconnected pieces. Then you can say that each one of these disconnected pieces is a different cluster. So it's an iterative algorithm. First, you square the matrix, meaning that every vertex tries to initiate a random walk from itself and takes one step out. Okay, then you say, all right, now I'm going to look at how much has been accumulated, and for every vertex, I'm going to look at its connections, so far accumulated probabilities, and I'm going to element-wise square them. What does element-wise squaring do? After you normalize it, the sum of them is equal to 1. And if you square an entry between 0 and 1, the smaller ones will be really, really small. Right? If you have 0.5 versus 0.2, the difference is maybe a factor of 2.5. But once you square them, the difference gets much bigger. The one that's square root of 2 goes down much faster than the one that's square root of 5. So that kind of separates these values, and then you can prune it based on either an explicit threshold, like the epsilon graph definition we defined, or you can just say everyone can have only k connections at most. And the proof of this is actually relatively stable. These values do not affect significantly the resulting clusters. It just changes the convergence speed. Eventually, you'll still arrive at the same thing, unless your pruning is too harsh. Okay, so these are what you do. And unsurprisingly, the most expensive part of this algorithm is the expansion, where you're squaring the matrix. Go ahead.
Oh, yeah, it seems that I saw some similarity between this and finding a strongly connected component in the DAG. Yeah. Yes. Yeah. So is there why do we use a random walk here instead of just perform a DFS or BFS?
But the graph is connected.
Oh. Okay.
So DFS will just visit everyone, and then.
So it won't reveal every edge between the two.
It will just touch all graph, and it won't tell you anything about the clustering.
Oh, okay. I see.
You have to basically, the intermediate steps we take here is such that we transform the graph into something where the clusters can be revealed by simple connected components. Because initially everything is connected, but we know that certain connections are between clusters that are only loosely connected by a few edges, and we're trying to basically get rid of those edges so that the solution here, what we achieve on the right, you can look at that and say that each one of these connected components is a separate cluster. So the whole transformation you're doing in between is to be able to come to that point such that a BFS or DFS makes sense anymore at that point. Okay, expansion is a random walk. You keep squaring, so that's kind of expensive. After each squaring, you sparsify the graph, and I explained how you do that. You basically prune certain entries that are smaller than a threshold, or you say that only keep the k largest ones for each column. Okay, so the problem here is you can't even, in general, square A. The matrix, because even if you're going to prune it later, temporarily it's too big. Because if you have 1,000 connections from every vertex in general, squaring it will create 1,000,000 connections temporarily before you prune it. And having 1,000,000 connections for each vertex on a large graph is even challenging for supercomputers. So think about graphs with hundreds of millions of vertices, not some toy graph. And these are the kind of graphs that we worked on. So the idea is pretty simple. The solution to that, instead of forming the pruned output all at once, or instead of forming a square all at once and then pruning, you basically form subsets of columns of a square and then prune it immediately and then go to the next subset and then prune it and go subset. So you can choose how many of these columns you're going to create at once on a square, and that depends on how much memory you have. But the trade-off is clear. The smaller the B is, the less memory you're using temporarily, but the less parallelism is in there, because your operation in the extreme case, where B is equal to 1, is no longer matrix-matrix, you're doing a matrix vector, and we know that it doesn't have a lot of parallelism in there. So you want to increase B as much as possible given your memory constraints. And one code that I worked on does exactly that. But you'll see what the problem there is, and there's actually room for improvement for anyone that wants to work on this. The individual algorithm that we use for this A times, for example, A underscore B part is a sparse version of the summa algorithm that you've seen in the dense linear algebra class. Basically, it's a two-dimensional algorithm. At every stage, the people broadcast to their processor columns and processor rows, and the owner computes the local update. You've seen the summa algorithm, and you have to do this thing for each phase. Phase is defined as how many times you have to do this to finish forming A square completely, or the C completely, and there are n divided by B phases. So the downside of this algorithm, even though it works right now, is you will be repeatedly broadcasting the first matrix phase as many times as there are phases. You don't need to. This is the extra communication you just do so that you limit the memory consumption. There might be better ideas to do that, and some of them are in the brewing. But if you're interested, talk to me, and we might carve a class project. There is more steps than matrix multiply, sparse matrix multiply here. There is a k selection algorithm, because at every pruning stage, we choose the k smallest or largest entries on each column. And we'll talk about selection algorithms in parallel in the sorting and searching lecture. So basically, how do you pick the k's largest entries in a vector in a parallel environment as fast as possible? Some pruning, which is more or less embarrassing the parallel. There's connected components, because once you come to this final end of the iterations where it converged, you have to now be able to visit every connected component separately and output them as if they're the clusters. Right? So that's a problem that needs to run in parallel as well. It's a fundamental graph algorithm called connected components. We won't talk about them this year's lecture, but maybe in the future. And there's lots of challenges of I/O. I won't talk about its scaled well. Questions? Okay. I think I'm pretty much good on time. The last item I want to talk on supervised learning is probably an application you won't find a lot in standard textbook machine learning. It's called sparse inverse covariance matrix estimation. Anyone heard about the term? Good. Maybe it's because it's a mouthful. Anyone heard the word graphical model? Heard. That doesn't mean you have to understand it. Okay, good. So this is one way to estimate graphical model structure. So this is also called precision matrix. Let's say you're trying to calculate correlations between data points. The straightforward way of doing this is you calculate a correlation using a Pearson correlation, a standard metric of, and then you define some sort of similarity, some other similarity metric, right? But it might be the case that you want the actual partial correlation. What is partial correlation? You want to see if these two events are really correlated to each other if you take out the effects of all other events. And here's a picture I found in an obscure paper, which I like, the snowman thing, okay? If you're just looking out and say, is the number of snowmen correlated with the amount of traffic? Well, yeah, but it's only globally connected. Why? Because it's true snow. Whenever there's snow, both the traffic increases and the number of snowmen increases. If you regress out the effect of the snow, inherently there is no direct connection between traffic or snowmen. It's only indirectly connected through a third entity. It's called snow. So you try to regress out all the confounding variables when you're building a partial correlation input. So that's you can understand basically intuitively why this might be very important. Especially you can think of health, right? You know, drug discoveries and all that stuff. Is this drug is actually affecting this situation, or is this just because of a third other side effect? Is it really inherently helping, or is it just coincidence? So one way to find these partial correlations is you get the you compute the inverse covariance matrix. And whenever there is a 0 in there, it's often that there is conditional independence. These two items are conditional independent once you regress out all the other elements, right? So, good. So here's one algorithm we're going to study how to do that. And by the way, I should say that usually you don't directly get zeros once you solve this problem. You get things really close to 0. And to achieve actual sparsity in practice, we enforce this regularization term as I described, you know, like either L1 penalty, you penalize having too many non-zeros, or L2 penalty, which is the square of entries. So somehow you try to recover the sparsity structure by enforcing it through regularization and penalties. Okay? The formula is mouthful and it's not important. And a bunch of applications in biology I like listing here, but I already gave you, I think, what I want to talk about most, which is what I want to think about this is finding effects of drugs without the confounding variables. Very large algorithm description, and you don't need to even look at this. All you need to care about here is there's a bunch of blue lines here where most of the time of the algorithm is spent. It's a pretty principled algorithm. It actually doesn't even assume the data has a nice Gaussian distribution. It will still recover the structures. But it's very expensive. It's iterative. You see that there is actually 2 loops within each other. And within the most inner loop, there is a bunch of distributed matrix multiplication. One of the inputs is sparse, one of them is dense. Okay, so that's basically where most of the time is spent. And so how can we make this algorithm go fast? If we know that there is a really expensive innermost piece, we can apply the implicit parallelization idea and say, how can we make sparse times dense matrix multiplication efficient on large scale? And that is the distributed memory solution in this case. And you know, basically you study all possible distributions. In this case, the regime is much larger than dense matrix times dense matrix, because often the sizes of the matrices A, let's say you're multiplying an A sparse matrix with a B dense matrix, it really depends on how much sparser A compared to B, and what are their relative dimensions. The 2D algorithms usually suffer because one of these matrices has much more non-zeros than the other, often the dense one does. And treating them as equal and then communicating both of them at the same rate is not a great idea. So here down you see on the x-axis is the ratio of the non-zeros, right? And if this is 100%, it is often the case that for example, for large scale, the standard algorithms like 3D algorithms are somewhat okay, right? This is the whole area. Forget about the colors for a while. Just looked at the black boundaries. If both matrices have the same number of non-zeros, if they were both dense, we know that 3D algorithms are great and they work very well, but when they start becoming more and more skewed, often different algorithms, what we call 1.5D algorithms, are best in terms of communication and performance. And there's more in the paper, and it does actually make a big impact. Especially if you remember the communication avoiding algorithms lectures, you can increase the K, which is, I'm not going to confuse Ks here for a while, and get more performance, but here you do the same thing in 1.5D algorithms, and each one of these lines, except the black one, is run on a different number of processors. So the red one is run on a single processor. Yellow one is 4, 16, and the time is on the y-axis, so you can see it's beautifully scaling. Questions? All right. I will conclude the machine learning section, and we'll go a little bit to the graph partitioning and see how much we can go, or whether any of that needs to spill to the next lecture. Graph partitioning has lots of cool ideas, but it's becoming more and more clear that unless you want to do research on this topic, you're better off using one of the existing tools. And then if you want to do research on it, I can give you a separate lecture. Okay, so, but you have to understand the main problem, right? So we will probably not cover all of these, so no point in going there. The definition of graph partitioning is really abstractly defined. You're given a graph that I described, edges and vertices. You are trying to separate them into P groups. You define the P, right? And usually there's an objective function. And often for this particular application, it is the communication volume. If you're doing some certain operation, and I haven't yet defined the operation, given that operation, you can define what is the cost function. And most graph partitioning software will allow you to perturb that cost function. If your operation on the graph is different than the default that the software assumes, you can change that. You can say that for every edge cut, I am thinking this much is communication is happening, or I want to penalize it differently. You can weight these things. That's totally fine. Right? An application is probably useful. So here's one partition. Let's start with this. This graph is partitioned into 4 groups. And the numbers, let's not worry about them for now. You can also define them in some sort of balance constraint. You can both say that everyone needs to get more or less equal number of vertices, which is often the case, but you can weight them. You can say that this vertex has a weight 8, the other one has 1, so now balance it with the sum of weights, right? So you can basically, you're telling the software you can assign different number of vertices for each cluster, as long as their weighted sums are more or less equal. Applications, I think the driving application originally was telephone network design by Kernighan. Do you recognize this name? Kernighan? They have an old C language book. He has a very popular C language book. It's somewhat crazy that these guys have both worked on graph partitioning and C language, wrote the most popular C language book. It's weird. But anyway, that's the same guy, in case you're wondering. I know the C language books are no longer popular. So he was trying to design the telephone networks with minimum number of lines crossing. So because each line costs something, so he's trying to group things in such a way that he'll pay the least amount of money, or whatever company was employing. Let's assume it's AT&T. It's all the smart people at the time was employed in AT&T. In scientific computing, the classical application is sparse matrix vector multiplication. You can exactly define the communication volume of sparse matrix multiplication, not using graph partitioning, and this should be one takeaway from you. It doesn't exactly model sparse matrix vector multiplies communication cost. It makes an approximation. But a generalization of this graph partitioning idea called hypergraphs models it exactly. and then whatever way you solve it will minimize the communication volume in a distributed sparse matrix vector multiply. And the 80s application was a very large-scale integrated circuit layout. Again, this is an economic problem too there. You're trying to design the circuit such that minimal wires cross. Same problem like telephone, except on a different scale. And then, in Gauss's sparse Gaussian elimination, it actually is used to increase parallelism and decrease fill-in. Because you can convert most of the partitioning algorithms to an ordering algorithm by sorting them with respect to the partitions. And let's stick to one example so that you have a concrete one, right? And this is A, and you will compute A times X. Let's assume the input is sparse and symmetric in this case. And you only can do assignments of rows to processors. You're not allowed to randomly assign edges to processors. You're basically asked to assign rows to processors. And how would you assign it? So if your partitioning software returned you these 4 partitions, here is the graph representation on the right, and on the left you see the matrix representation. So now you can see what's going on here, right? All these diagonal blocks over here, they do not create any communication because this is local. The communication happens outside this diagonal block. Whenever there is an entry on this diagonal block, there needs to be some communication. Why? Because 1 and 2 are owned by processor blue, and it needs to get access to vertex 3 because there's an edge between 1 and 3. And it needs to get access to vertex 4 because there's an edge between 2 and 4. So anything that's off diagonal block and non-zero requires one communication. And once you nicely model this thing as a graph partitioning problem, and the cut will give you some sort of approximation to how much communication is going to happen. Right? At least it will give you the communication on the symmetric case if the implementation was naive enough that it would create one message per each non-zero in there. But in practice, it's doing something a little wrong, and here's why it's doing wrong. So think about this vertex 6, and the processor, red processor. Red processor needs vertex 6, but the model thinks that it needs it twice because there are 2 edges cut. But in practice, it only needs it once because there's no point in sending 6 twice to the same processor. It can store it and use it for both computing 3 and 4's updates. Right? So that's where the graph approach is slightly problematic. It doesn't include these cases where one message would be enough for all the recipients within that processor. But it's an approximation, and the reason it worked well over years is most of the graphs that were partitioned were in scientific computing. They have nice bounded degrees. So the error you're making by having a graph assumption here was not big, it was bounded. But if you're working on, let's say, social networks and using this idea, the error can be unbounded. There might be a vertex here that's connected to everyone, and you're overcounting by pretty much order n. You can be overcounting by order n, and that's a huge approximation error. In graphs that are coming from scientific computing, usually this is bounded because there's a physical reason of this boundedness. All right, so what's the cost? I defined the problem, but the solution is not easy. And trivial approaches, of course, are exponential. You can try every possible, n choose n over 2 possible partitionings in a factorial space and try every one of them and find the optimal. Obviously not great. But you can also say that it's not just because I'm stupid this is hard. It's also NP complete. It is provably hard. Right? But we have good heuristics, and most of this lecture is going to be based on heuristics. The first heuristic is really graph bisection. It's a general idea that applies pretty much it can apply to every partitioning algorithm. Whereas instead of trying to solve a problem k ways, like try to partition it directly to k pieces, just recursively bisect to 2 and recursively bisect to 4, 8, That's fine. So that makes life manageable, and algorithms are easier to implement that way. And then the second tool that you often use, a concept that you have to understand, is a separator. So if you can find a certain number of edges or vertices that will separate this graph into two pieces, right, you essentially solved your problem. The graph partitioning problem will be solved if you can efficiently find the so-called separators. In this case, the red vertices in this mesh is a vertex separator. Why? Because it separates the graph into two pieces. And in fact, it's one of the best ones. A lot of these vertices are best because this is a regular mesh. Problem is easy when you have a regular mesh. So what I can do, one algorithm I can do, and maybe I'm talking about this a little too early, is, well, maybe it's in the next slide. There's a concept of edge separator and vertex separator, but don't worry about it. You can always go from one to the other. If you're given a vertex separator, you can just get all the adjacent edges to it and define an edge separator, and vice versa. You might lose a few constants, but as long as your degree is bounded, it's on the same order, asymptotically the same thing. Okay, so here's the main idea to how to generalize this separator thing and find a graph partitioning algorithm. This one will actually ignore more or less the edges. It will look at the coordinates only, right? So what are we going to do? There's a nice theorem that says, this is due to Tarjan and Lipton, that says any planar graph, for any planar graph, you can find a set of vertices that's on the order of square root of n. It's only square root of n number of vertices compared to order n of the input. That will split this graph, planar graph, into two pieces, where each piece is not horribly load imbalanced. One of them is at most twice as big as the other. So one of them will be 2/3 of the graph, the other one is really 1/3 of the graph, in the worst case. That is actually almost as good as regular meshes, right? In the regular mesh, if I split it right in the middle using these red vertices, what I'm getting is a separator of size square root of n, right? And then it's giving me perfect balanced stuff. Basically, if any planar graph, this is almost true, is what it says. And the algorithm you go from here is called nested dissection. And I'm going to use this mesh because it was actually first discovered as a mesh. What you only need to do is find a vertex separator, split it into two, recursively call the same thing, right? And then if you look at how much communication you just introduced, the actual results are pretty good. You just solve the recursion, and then communication is pretty minimal, as good as it gets, and you can lower bound it. You can't really find a better separator. So for planar graphs, the problem is well solved using the vertex separator theorem and the nested dissection that follows it. But here's another way to do that. It's called, do I want to talk about this? Well, this is nice too, okay. Here's one algorithm that doesn't use, another algorithm that doesn't use edges. It's called inertial partitioning. So the idea here is you're given a bunch of points on the right, and let's say if I project these things into some line, and I haven't defined how I choose that line, if I project these points to this line, and then find a median on that line, and split it based on that, I'll get a partition, right? Is this partition good? Well, it depends on how I choose the line. Okay, so why am I saying this is coordinates only? This doesn't use the edges at all. It just looks at the data points on XYZ space, and does the partitioning based on that. For problems where that come from physical domain, that might be okay. For problems that are based on, again, social data, internet data, this might not make sense at all, when you don't have even physical coordinates in some cases. But so basically this whole problem becomes, how do I choose L? And the reason it's inertial, there's a little bit of a reason. So imagine two different ways of choosing L. If you're given this rectangular, weirdly shaped mesh, And so on the left is probably the right thing to do, because once I choose L, I'm going to project the points to L, and I'm going to cut it in such a way that there'll be only 4 edges cut. But if I am unlucky or I have a bad way of choosing L, I can choose L such that it will, the perpendicular line that will cut the projection will cut, I can't even count, 14 edges, right? So I need to find an automated way to choose the L on the left. And that's called inertial partitioning. Mathematically, what you're doing is you treat every single point as if some data, and then you find the least squares fit to it. And that's fine, right? And the reason it's called inertia is not because of that, because of the physical meaning. If you think about these points are able to rotate around this line, you're basically trying to find the case where you minimize the inertia. Okay, and then you choose a line that will do that. But I like the least squares definition more. You basically find the line that makes the least squares fit to this data, and then use it as your L, project it, cut it. And then lots of ways. The mathematics says 2 by 2 eigenvalue problem in 2D, 3 by 3 eigenvalue problem in 3D. That's basically how it's solved. All right. So nodal coordinates is fine if your problem is okay with it, comes from a physical domain. Connectivity structure follows more or less the nodal coordinates. But if you have an input that looks like this funny snake-like structure on the right, and if you ignore the edges, you'll find a horrible cut, because the best cut there is only one, right? You can just cut one edge and split that snake into 2, but the nodal coordinates that ignore the edges will probably cut 5, 6 edges. So again, you need to understand a little bit about your problem before you have direct blindly apply these. Now we said partitioning with nodal coordinates, and there's one that actually ignores the coordinates completely. And just looks at the edges. So that is coordinate-free approach. Kernighan-Lin algorithm is easier to describe, not very easy to describe. Okay, there's a nice historical note. In addition to the book, apparently Kernighan invented a couple of more things. Thanks for these notes. The name of Unix is based to him, apparently. I didn't know that. And have you used awk, the text processing thing in terminal? Okay, the K there is him, the last one. It's good. I mean, lots of things. When the computer science was a wide open field, you can make contributions on a wide variety of topics. So what is this algorithm about? This is an iterative swapping algorithm, meaning that it starts with some random initialization of partitions, and then it tries to calculate how it can move subsets of vertices from one partition to the other in a way that will maximize the gain, in this case, which means minimize the maximizing the gain of the cost of the partitioning, right? So the objective function is the minimum number of edges cut, and every time you swap vertices, you're hopefully decreasing that number of edges cut, and then which swap is the best. So there's like, and choose 2 different swaps you can think of, but it's beyond that. You have to consider sequences of swaps, because the algorithm doesn't do one swap at one phase. It tries to do a sequence of swaps, and then tries to find the sequence that's best. The original implementation, N-cube, is very slow. There is a fiducia metices re-implementation. Algorithm is a little too complicated to describe in class, but the cost is went down drastically from N-cube to linear time on the number of edges, which is great. I don't even think I have time to describe this, but just a general idea. For every swap, what you need to calculate, you basically need to keep a bunch of variables to be able to calculate the new cost. The old cost is the edge partition. How many edges are crossed between 2 partitions? If you're going to move a subset to another one, you have to basically calculate how many new edges I'm introducing, how many external edges are becoming internal and no longer cut, and what are the partition edges. So you have to keep track of these variables for every change, and these are defined in E, I, D, and then you can use this very efficiently to calculate the new cost. Right? And the algorithm is this fancy thing, but I have a much better way of describing it. So here's what's happening. It says fiduciary thesis, but the same idea applies. Let's say you started with some initial partitioning, black and red groups, and now you have to calculate the gain if you were to move any of these vertices from one side to the other. Okay? So these gains are written next to the vertices. The vertices use letters, and the numbers are the gains if I were to swap them to the other group. So if I swap vertex G to the red group, I gain 3. That's the maximum, so I do that. And then I have to recalculate stuff, because once I swap G, the gains of other vertices will change. It doesn't stay constant. I can efficiently go over and update their gains, and I do that. So the numbers went from -1 in C to -3 over here, okay? And then I choose the next one, and what is the next one? It turns out it's F. Then I need to move. Well, that's interesting. Okay, no, it's not F. It basically says, what is the cut size? Okay. Okay, fine. The reason we can't choose F is because we try to keep these things balanced. So you do swap from, if you first chose a swap from red to black, now you can't make the second swap from red to black too. Now you have to choose a black edge. And the black edge with the maximum gain is D. So basically choose that, and then continue until you visit every one of these vertices. You get a nice sequence, okay? But you don't move them permanently. You just make it like, if I move this, what would happen? So the hallowing of these vertices is just saying that, I tentatively moved them. The algorithm shouldn't reconsider them yet until this phase is over. And what will happen? So you get a sequence. So what does the sequence tell you is, after every swap, in the parentheses, I'm showing the new cost of the partitioning. So it initially was as bad as 8, then it went down to 4, but then after those swaps, I'm not gaining anything. My swaps are getting worse, 5 and 7, but I have to do this because I don't know if it's actually going to go down again or not. So I run this whole sequence, and I then look back and say, which was the best point in the sequence to stop? And it really turns out that after you swap G and D, I should have stopped. And I roll back the last couple of changes, and I accept that and go to the next iteration of the fiduciary thesis or kernel. So that's the iterative swapping. This is almost never used on a large graph. This is too expensive. But this is almost always used as a subroutine on other algorithms. And so good to know something. And also for iterative refinement. Anyway, it worked on him because he had a graph less than 360 vertices, and apparently he saved the company quite a bit of money. Spectral bisection. I do want to skip this part, and you can read this, but I gave you the spectral Laplacian idea in the clustering part. One of the reasons I want to skip this is because I want to give you the high-level idea about multi-level partitioning, which made this whole graph partitioning idea feasible in practice. Okay? So let's skip the bisection. But hey, I promised you to show you one picture. Okay, so if you're given a mesh on the left, think of the picture on the left. They're actually the same. One of them is just, one partition is color-coded, not color-coded. In black and white, dot-coded. And if you look at its second eigen, the V2, the second eigenvector, from the correct directionality, you see that it actually reveals how you should be cutting this thing. I'm talking about this ribbon-like shape on the right. So that's basically one of the things the algorithm is doing. And I talked to you a little bit about the Lanczos algorithm to find these eigenvectors, and didn't give you the full code. Here's the full code. Again, full code means that doesn't mean that you have to implement this, because in practice, Lanczos is a complicated process that might break down, and it needs to be restarted and so on. Use your software as opposed to just copying this 10 lines and hoping that it will converge. Probably will not. But it's a good place to mention one reality here. So we are in the graph partitioning class, right? And we're talking about an algorithm called spectral bisection. We didn't give details, but it's very similar to the clustering. But we say that in order to find this algorithm to work, for this algorithm to work, I need to calculate some eigenvectors. And the way to calculate eigenvectors is to do sparse matrix vector multiply. It looks a little bit of backwards, right? So did we ever gain anything? Because we started the graph partitioning with the motivation to solve sparse matrix vector multiply efficiently, and now we created a subproblem that needs to solve sparse matrix vector multiply. Right, so this happens in computer science often. You bootstrap it, right? You say that the original problem is the expensive one, I need to do thousands of iterations. But Lanczos converges after a few iterations, and I can afford to do a couple of Lanczos which is not balanced if my goal is to be able to get a solution that will improve the other problem that I'm trying to solve. So bootstrapping, in some sense. But you understand the chicken and egg problem. And the second chicken and egg problem that also needs to be understood is we're doing this for parallel computing. We usually graph partition so that we minimize the communication in sparse matrix multiply, minimize the communication on some other task. But all the algorithms so far I talked about I'm describing it in serial. So there's a challenge. Some of them are parallelizable. Some of them are really hard to parallelize. And I'm not going to touch that aspect because it's a whole research area and a little more convoluted. But I need to leave you with the big idea, which is the multi-level acceleration. So this algorithm we solve, Kerning and Lin, might iteratively improve things a little bit, but it's usually too expensive. Most of these algorithms are too expensive or too much memory consumption. So what you do is this thing called multi-level partitioning. You're given an initial graph. You say, I can't solve this directly. Instead, I'm going to get an approximation to this graph, smaller, and continue until it's small enough that I will solve it at the bottom with some algorithm. It can be even an exact algorithm if the graph you eventually get at the bottom is small enough. And then I'm going to project back that solution. What do I mean is this picture. It's very popular in this area. It's a V-cycle. You start with a graph, and then you define some way to coarsen this graph. I haven't talked about what that is. And then if you come to the smallest graph that you think you can handle, then you solve it either exactly or an algorithm you trust. And then you project it back to the next fine level. You can keep these mappings. And in that area, you have to do a little bit of iterative refinement. And that's where usually you use this Kerning-Lin idea. Because you have a good warm start when you're projecting back, but it's not exact on the fine graphs. So you can do some swapping to optimize it and do it again. So this idea impacted, had such an impact. I think the authors of the first paper, Chaco, in 1995, got a Test of the Time award on supercomputing a couple of years ago. And it created like 5, 6 different software, all computing using the same philosophy. And each one of them are widely used in practice. Okay, so there's different ways to do this. Coarsening, and I don't have time to explain all of them, but I'll describe one of them, okay? So one of them uses maximal matching. You're given a graph, and I'm going to talk a little bit about matchings on graph algorithms. So what is a matching? You're given a graph. A matching is a subset of edges such that endpoints do not intersect. So you choose a subset of edges such that no endpoints are shared. A maximal matching is such that you're given a set of edges that form a matching, and you can't increase the size of that set by adding another edge. You see the difference between maximal and maximum. Maximum means overall possible edge subsets that all define matchings. Which one has the highest cardinality? Maximal just is a local maxima. You're given a set of edges that define a matching, and you cannot add another edge to it. It might not be the global solution. It might not be the best subset, but I give you a bad input. Like I say that this is a matching of 4 edges, and you can't make it 5 because it's a local optimal. But there is a 5 edge or 6 edge matching if you started from scratch and ran a different path. But so maximum is expensive, although a polynomial. Maximal is almost always linear time, pretty easy. Getting stuck in local optima is pretty easy. You know, greedy algorithms exist, lots of other names exist. A simple greedy algorithm works just fine, and we'll do that. And then you'll get a matching like this, right? So the red edges are the matching. And now you can see how you can go from here to a Coarser graph. So these pairs of vertices will form your new vertex in the next level. And if your matching is close to optimum, you'll shrink the graph size by a factor of 2, more or less, right? So you keep doing this. This is your coarsening scheme, right? And then details. Here's one way to do this, the computation. Once you find the matching, how do you actually do this? A nice principled way I like to do this is to multiply matrices. If you represent each of your matchings as one row of a sparse matrix, you see that's why there's only 2 non-zeros in each row on the left matrix. And you use that matrix on the left and transpose of it on the right. Once you do this triple product, it will automatically compute the correct weights in the Coarser graph. And you can actually use this triple matrix product idea to form your Coarser graph once you're given a matching. It's a nice, neat algebraic trick, but pretty much that's what it is. Okay, and then you can apply the reversed mapping to get the finer partition. As long as you preserve those mappings, it's not hard. There's another way to do that, but I would rather skip it. The other one is based on maximal independence set, another graph concept that will define subsets of vertices that are not neighbors of each other. And that's actually intuitively makes sense, right? If you choose subsets that are not neighbors of each other, you can declare each one of them as its own aggregate in the next stage. Each one of them will define a coarser vertex in the next level. And then we'll actually see maximal independence set example in the graph class. But I want to leave you with one example, one important thing, sorry. This is the available implementations that I know of. There's probably more. There's available implementations for Kernighan-Lin, exist in popular software tools, geometric and spectral partitioning toolbox. I hope this link is still working, but it's GitHub, it probably is. And then there's big packages that have a lot of different softwares. Kayip is probably from Kashtul KIT Institute of Technology. Zoltan is from Sandia. But I want to tell you about one thing that's a hypergraph concept. So we started this lecture saying that sparse matrix vector multiply is not exactly solved. The communication cost is not exactly modeled with graphs. And why we said this was happening is because when there is an edge like this, like when processor 1 needs to access V7, you're double counting because there's 2 edges that are cutting, right? And how does this get solved if you want to? If you want that much exactness, is something called a hypergraph, where each edge in a hypergraph can connect more than 2 vertices. It's instead of binary, it represents any k-array relationship between vertices. And you define your hypergraph this way. It connects multiple vertices, and a cut becomes an exact cut. So the number of hyperedges that are cut between these 2 vertices, two partitions, is exactly the communication you need to do. Exactly. And it's expensive. This will give you some know about this, and know that there are tools that do hypergraph partitioning if you care about quality. But so here's one example. In a simple example, it's actually not that effective. It's just 10% better. But in really skewed graph, it can be arbitrarily better. But it's usually almost an order of magnitude more expensive to run it, because hypergraphs are quite general data structures where they don't accept a lot of efficient algorithms.
So what is the hypergraph here in this case?
In this case?
No, in the next one, the example.
Oh, this is, I have to basically, the hypergraph is the same thing, right? You just define for each, the definition of hypergraph is the same.
Yeah,
right?
What edges do you include?
So
hyper edges.
So the way I like to think about is the matrix. So I define the matrix of this connection, right? So if this is pairwise connected only, this Cartesian grid, right? And how many vertices are in there? Let's say that this is n by n, there are n square vertices. I convert this into a sparse matrix like this, and I define each row as a vertex and each column as a hyperedge. That's a nice way to think about it, like how many different connections are in there. But okay, I'll give you a direct answer. Every vertex here is probably connected to 4 neighbors if it's only for 5-point stencil, or it might be connected to 8. I don't exactly know what the example's connectivity structure is. If everyone is connected to its 9-point neighbors or 5-point neighbors, each one of those 9 points will define a hyperedge, the connectivity around that vertex.
Okay, so it's not like what you want for matrix multiplication to propagate. It's just a grid, basically.
It basically, if you cut it, it's trying to model, let's say if you cut this, the edges between the vertex on the boundary, green boundary, and the red boundary, if you try to cut it, how many different messages that you need to create? It's just trying to model that, right? You have a hyperedge there with a connectivity of, let's say, here 9. So if you cut that hyperedge, you need to send a message between the green processor to the red processor. But why is it correct? Because you need to send one message. Only one vertex information needs to go. If you model this as a graph where there's 3 connections up, the graph model will think that you need to send 3 messages. But in fact, you need to only send 1 message because only 1 vertex is cut. So that's why hyperedge is correcter. Thanks. I mean, I actually didn't think about going back to the graph on this case, but thanks for reminding. And so it's not a big difference on this graph because it's the most regular graph you can think of. But if you take graphs that are unsymmetric and weird, you can get like significantly better load imbalance ratios and significantly lower communication volume using hypergraphs if you're willing to pay the price of expensive cuts. Okay? Cool. Any other questions? You're not convinced? It's just another tool. So some people, if you are solving some problem for manufacturing, you'll make a chip, millions of chips. There's a little bit of quality matters because of the multiplication factor. But if you're just solving a scientific problem once, maybe that doesn't matter. You don't want a little bit of better quality. You just want to get it solved as quickly as possible. That's one of the reasons why hypergraphs didn't come from scientific computing community. It came from the VLSI, very large scale integrated circuits community, because they're manufacturing and every little bit of wire counts when you multiply with millions. So.